Yeah, so today, Professor Hanns-Christoph Nägerl from University of Innsbruck in Austria is going to deliver his second lecture. So, Professor Nägerl, so please go ahead.
Okay, thanks a lot. Yeah, so yeah, also I listened to Stefan's talk just a few minutes ago. Yeah, and it actually gave me a lot of remembrances. Yeah, you'll see a little later. Yeah, why. So anyways, ultra cold molecules. Yeah, so we are talking about here now neutral molecules, and we are talking about dimer molecules. And let me pick up or pick up where we left off yesterday. So we are talking about molecules, simple molecules, dimer molecules, as you will see later, that we in fact make out of atoms. And here's the list of reasons why we do this. And Stefan Village just gave you a few more reasons why this is interesting. I don't go back to that. So just the case of rubidium cesium. Here is the full Hamiltonian, if you wish. So you, in principle, can control the position and the angle of the dipoles. In principle, you could also think about whether you can actually have different directions of polarization for the molecules, but I think that's difficult to realize. But anyways, rubidium cesium has a well-sized dipole moment, yeah, on the order of 1.3 dBi. And that's, I think, very nice for the lab because you don't need that high electrical fields to polarize the molecule. What other options are there? We briefly had this slide already yesterday. KRB is an option, a very nice option. It is it has the possibility that this is a fermion actually. When potassium is a fermion, then the KRB molecule with rubidium being a fermion will be a fermionic molecule. Situation is similar to KCS, where cesium is the boson and potassium can also be a fermion. Admittedly, in Innsbruck, we are working hard on actually still the bosonic version, where potassium 39 is being used. I won't report about that at all, but we're working hard and hopefully at some point we have some results. One very nice molecule, dimer molecule that I should mention that has a very high dipole moment is lithium cesium. And it's being pursued, as far as I know, in Heidelberg and in Cheng Chin's group in Chicago to some extent, but I don't know how far the efforts are towards turning these into ground state molecules. And a bit off this line is rubidium strontium, because strontium is not an alkali, it's an earth alkali, as you know. And so this is it's already opens up a different route, because rubidium strontium now is a molecule with not just a magnetic, with not just an electric dipole moment, but also a magnetic dipole moment, because of the rubidium atom and the strontium electrons being paired up. So that's actually also a nice option. Turns out that this is for sure not easy. The resonances to produce rubidium strontium seem to be rather difficult to handle, rather narrow, but I think we will see some results there also in the near future, yeah. So, and then for testing purposes, we have also been working here in particular in Innsbruck with homonuclear molecules, and I will come to that briefly because yeah, I mean, it's a simpler system, yeah, but we, in fact, were able to achieve good control quite early on with, in particular, cesium-2. Yeah, so anyways, yeah, so let me just remind you what we mean by a molecule. So I will actually talk about the weakly bound molecules, or basically atom pairs, in a second. With a very large internuclear distance, basically set by, if it's an atom pair, it's set by the size of the trap. And that's actually already quite tight, 15 nanometers in a lattice trap. That's the typical scale. But we want to create molecules in the very ground state, and the very ground state means the comic certainly here. You'll see a bit more precise potentials in a second. in the low vibrational ground state with the size of angstroms and a binding energy actually of roughly half an electron volt. Yeah. So what we will have to do is to turn our atom pair into this tightly bound, chemically bound, covalently bounded molecule. Yeah, so here is what we did over the years in Innsbruck. This is now a bit focused on our Innsbruck endeavors. This everything started with turning molecules, atom pairs into weakly bound molecules. This is started in 2003, and I should say, I think in the school I should say these comments. It actually started a bit like an accident. Yeah, we found by accident that our atoms in the BC were actually, we found that they were quite stable in the beam of our multi-frequency laser, trapping laser. But the weakly bound molecules actually that we then produced were actually not stable. And it's not because of collisions, as I will detail in a second. The loss was really quick, and that actually brought us to the idea, well, this molecule, these weakly bound molecules actually are susceptible to optical transitions. Okay, so now we have to remove that binding energy, and that's actually when we had first results on homonuclear molecules in 2008. And it's been since then an endeavor, and it's still ongoing, certainly. Yeah, actually, I think the real high times will only come now and soon. Yeah, and actually, I mentioned that already. You will hear nice, very recent results from Jun Yi tomorrow. So now let's focus quickly onto this ground state. It's a bit more complicated than the picture here. This is certainly the vibrational ground state. Yeah, is indicated in this comic. But it's also there are also rotational degrees of freedom. Yeah, that's actually certainly very nice, very helpful. But on top of that, there's hyperfine structure. So this is now the example of the homonuclear cesium-2 molecule. But you take any other molecule, KRB or rubidium cesium, and it will have a few dozens of nuclear states. Yeah, so hyperfine states due to the nuclear non-zero nuclear magnetic moment. And that's the manifold of these states. And in the end, what we are interested in is populating one of these states. In fact, that's doable, even though this energy scale, if you look vertically, is only on the tens of kilohertz sort of level. Yeah, but our transfer scheme is selective. Our initial state is well polarized and in a specific hyperfine state. And so we can, and then selection rules help also. So usually transfer only, the transfer that we'll be talking about addresses only 1 or 2 or 3 or so of these levels. And that actually helps, yeah. So, but anyways, yes, you have to, you can certainly start playing tricks with this ground state molecules. And I believe that Martin Zwierlein will talk about this more about coherence in these states and driving radio frequency or microwave transitions on these molecules. So let's talk come back to rubidium cesium. Yeah, and this is the specific situation. This is the ground state singlet potential, this triplet potential. Our initial Feshbach molecule that we create, as I will show you in a second, is mostly a triplet molecule, it turns out. And we have to convert that triplet molecule into a singlet ground state molecule, where we then have a sizable dipole moment. Yeah, so when I say on or off, off is off dipole moment, on is in the ground state. And this is the specific situation. We use an excited level with a energy above threshold here of about 6,000 wave numbers. That gives a wavelength around 1,570 nanometers. Up here, and then we go down, quote unquote. You will see how we do this. Actually, we never populate this state up here. Yeah, we do this in a 2-photon way without excitation of the intermediate state. This is done at about 980 nanometers. So that's, let me simplify this. So I'm certainly omitting all the other vibrational levels and so on. So in the end, we will be addressing a specific hyperfine state of that excited state potential. Actually, it's this triplet singlet triplet mixed AB potential that we're using here. This is an important detail in the end, because this, it turns out the state is strongly mixed and actually allows us to convert the triplet molecule into a singlet molecule. Yeah, so we need this accidental mixing here. I call it accidental because it's that's the way nature does it. Yeah. So, and we are choosing a suitable level here where we expect a large mixing, and where we also, just from eyeballing the transitions, where we see that there are strong Frank-Condon factors. Yeah, so I haven't drawn any wave functions here, but you can already imagine that the inner turning point of this level will match with this turning point. So this molecule actually here, the wave function will have 4 areas where its amplitude is enhanced. Yeah, whenever it sort of hits these molecular potentials, loosely speaking. And so we are actually using this enhancement here and there on this inner well here. Yeah, but you see this is an avoided crossing well. Yeah, so it actually caused by these 2 potentials. Anyways, yeah, so that took us some time to figure that out and to do all the spectroscopy and to be a bit lucky to find the right level. In fact, for KCS, we still need to identify a similar situation. We haven't done so. Yeah, so KCS is still in this sense open. So these are the 2 lasers, and I will just call the final state off. The final state on, the initial state is off, and there is this excited state in between. Now, how do we do this now? Yeah. Okay. After all this preparation. Yeah. So, and then the question is, can we make a condensate, a Bose-Einstein condensate of these ground state molecules? Yeah. So let's go back to atoms quickly. And we just heard from Stefan Village that atoms are simple and molecules are already significantly more complicated. So if you think about atoms with their simple fine structure split fine structure split excited states, you can find string transitions and do laser cooling, and even the hyperfine structure indicated here is not hurting you. Yeah, you might need a repump laser, but in principle this works for a quite large class of atoms, and it's possible because we have we can recycle our atom all the time. Yeah. So, and this works with many atoms by now. Yeah, I mean, it's not it's just certainly a fraction of the periodic table, but a significantly large fraction. Yeah, and if we go to molecules, we have this comic here where we have a lot of vibrational levels plus the structure that I just discussed. And so when you do an excitation, you are very likely to de-excite into some other level, and all your population will go away. Yeah, so that's for sure difficult, and we just heard from Stefan Village in his talk what one can do to some extent. Yeah, well, he's not cooling, he's not doing now the initial cooling. He was talking about the situation where you already have trapped atoms or trapped molecules, and where you then want to interrogate them. Yeah, so let me briefly remind you of what endeavors are there around for slowing and cooling molecules. Stefan mentioned some of that already. So one way that people are using is for polar molecules is what is known as Stark deceleration, pioneered by Gerhard Meyer. Actually, he's now back to Berlin. Yeah, he was away from Berlin for some years. He's now back. And this is a Stark decelerator, molecules coming out of an oven or source here and being Stark decelerated as they move downstream here across 1 or 2 meters. And in the end, they can actually be trapped in, for example, electrostatic trap. Yeah. So that works. That's been demonstrated. That can be augmented or combined with buffer gas cooling, where you have preferentially helium buffer gas to cool your molecular source. Yeah, and that has been demonstrated for some molecules with actually fairly large magnetic dipole moment, and the pioneering experiments have been done at Harvard in the group of John Doyle. Yeah, but temperatures so far are rather high. Yeah, in comparison to what we are aiming at in the millikelvin regime. And one for sure has to combine this with additional techniques. Yeah, so this won't work alone. And in particular, the densities are not high enough. Yeah. So we just heard from Stefan Bilic that you can do this also in ion traps with ions. Yeah, well, ions will not condense. Yeah, I don't think it's possible to overlap the wave functions of ions. It's actually an interesting question. Yeah, but I don't think ions can be condensed. But you want to, when you want to control them, actually you can do a lot. We just saw here pictures from the Drevsen group and Aarhus with magnesium hydride, for example, being co-trapped in this trap, in this ion trap. And also here, the temperatures are at best in the millikelvin range, yeah, in the millikelvin range at best. We just heard from Stefan how one can do sideband cooling, and so there are avenues, but this works on very small samples. And just for the record, because Stefan mentioned that, when I was a PhD student 25 years ago, we already saw co-trapping, most likely of calcium hydride in a calcium ion trap. We actually learned how to purify it, yeah, how to kick out these molecules, because we co-trapped up to 50%. Yeah, but we were interested in just a few calcium ions for quantum computation purposes, and you will hear about the ongoing experiments with calcium ions in Innsbruck from Christian Roos, in fact. Yeah, but the old history, long time ago, when I was a young guy, we already saw this, and then and that's also good to hear from the students. Yeah, then somebody told me, oh, this is all well known. It's been seen in the Wineland group. Forget about it. Yeah. So I forgot about it, but I put it, we didn't write a paper, but we put it in my thesis at least to say that there is something going on in these ion traps that's more interesting. And as you see, it by now is an entire field. So, and then you can co-trap ionic molecules and neutral atoms, yeah, overlap, for example, an ion trap for barium chloride ions with calcium ions. And that's been done in the Hudson group at UCLA, for example, and at some other places. So that's also a possibility. Yeah. And in fact, let's see how, actually, I don't know, but Johannes Hecker-Denschlag at this meeting will, I'm sure, talk about more of this. Yeah. So, but even also here, temperatures are rather high, millikelvin. Now, direct cooling of molecules has seen quite spectacular development over the past years, starting with the experiments in the group of Dave DeMille, that being picked up by the group of Mike Tarbert at Imperial College in London. And here's a highlight, this paper on molecules cooled below the Doppler limit. And this is a special molecule, calcium fluoride. It's what we call a diagonal molecule where one has essentially cycling transitions. Yeah, and this will probably be a very nice route to pursue also. Yeah, and that has a lot of possible applications. Yeah, so temperatures are below millikelvin for these experiments. They go into the microkelvin regime nowadays in recent years, but admittedly, the density is still rather low. So the phase-space density, PSD, is rather low still. Yeah. So certainly, I'm hopeful that this will also yield to high phase-space densities in the end. So what's the phase-space density? Well, as you all know, the product of the thermal wavelength and the density. And as you know, we want to push these experiments towards phase-space density of unity into the regime of quantum degeneracy. Yeah, so you have to watch both. The particle density has to stay high, and the relatively high, and the temperature has to be low. Yeah, so we have to do tricks to reach high phase-space densities. Yeah, and then to not lose, as I always say, yeah, phase-space density. So now you can say, well, why not start from ultra-cold atoms? In fact, that's been also an endeavor that's been going on for quite some years. Actually, the photo association is a nice way of going from ultra-cold atoms to ultra-cold molecules, and this has been done over more than 20 years by now. Yeah, so one can do this in one color scheme where you just have one laser and then you spontaneous emission takes you into some bound state, molecular bound state, or you can do this in a more controlled way where you have two lasers and you do either a pump dump scheme or perhaps something more clever, as I will talk about later. Yeah. In principle, this looks good. Yeah. But it turns out, for whatever reason, yeah, one can speculate a little bit, the densities done in the typical experiments, even in the ultra-cold experiments, and have not been really persuasive. Yeah, so this has not worked so well, and actually, I don't know why. Yeah, I have to admit, we've never done photo association. We'll do something else in a moment. So we actually do Flashback association. We've not systematically done that. I know that some groups have played with photo association and it works okay, but it has some limitations. Yeah, so one should say, and perhaps somebody else will demonstrate a better way. The densities are still rather low. Yeah, even though one essentially inherits the initially low temperatures from the atoms. Yeah. So, but I'm confident this will work out better in the future. Yeah. So now, what's the other way? Is actually, I mentioned already, is going via so-called Flashback resonances, and we already discussed what Flashback resonances are. And this shows a result from a long time ago where we have a Bose-Einstein condensate, and we outcouple from this condensate a cold sample, very cold sample, actually a sample in the regime of quantum degeneracy, initially at least, yeah, of molecules, yeah. And actually, but not trapped, actually expanding very slowly with very low rates, comparing rates at the level of nanokelvin, actually, yeah. And we call these molecules, because they are produced on the Flashback resonance, we call them Flashback molecules, although in our case, they're nothing else but van der Waals molecules. Yeah, this is the van der Waals tail of your molecular potential, and we call them Flashback molecules. So now let me simplify the Flashback resonance that I've shown earlier, just as a level crossing. Yeah, so here I plot the energy of two atoms horizontal, and the molecular energy to have some tilt. There's a certainly, I mean, it's only interesting if there's a difference in the magnetic moment, and the intersection point is essentially this Flashback resonance. Yeah, so as indicated here, as discussed earlier. Yeah, and so if you zoom in into that intersection point, there will be an avoided crossing. Yeah, so you have a sort of a situation where you mix your atomic state with the molecular state, and if you then go away from the resonance, you actually acquire some binding energy, and you actually create a molecule that's very weakly bound. Yeah. So this avoided crossing is in fact our entrance door into the molecular world by dynamically changing the magnetic field here in this picture from right to left. Yeah. In this case, for this particular resonance, from higher field to lower field. Yeah. So that's our entrance door, yeah. And in the experiment, we have an atomic sample here, just shown schematically, and we ramp across the resonance as a certain fraction of the atoms finds a partner, and that gives us a certain molecular fraction. When you do this in free space, the typical efficiencies are a few percent, up to 10%. And if you push it a bit, we've seen efficiencies up to 40%. But then, but that needs free space and another trap we've seen. Yeah. So from a BEC of 100,000 atoms, let's say. Yeah. So, but in any ways, that's very nice. So this is actually the picture that I just showed you before. Actually, what's being done to record that picture? Actually, we go back in magnetic field. And we bring the molecules above threshold. The molecules will dissociate back into atoms, and then you image them. Yeah. And how do you separate the molecular part from the atomic part? Well, this is done in a Stern-Gerlach type experiment by means of a magnetic force, so we apply this magnetic gradient while we have them after production, and then this force separates the two samples, and then you can, for example, remove the atomic part with usually a combination of microwave and light into other states, and then it's not resonant anymore with your imaging light, and then we get a picture like this, yeah, with only the molecular part. Here, certainly I just did a PowerPoint picture, yeah. Okay, anyways, yeah. So this is the way it's been done now for the past more than 15 years in various groups. And this is a gallery of the initial homonuclear molecules being produced in this Flashback way. Yeah. Okay, so what are the properties of these Flashback molecules, you might ask? Yeah, so we are actually here in one of the very last bound states. I showed you a spectrum of states already earlier, rubidium cesium. I'll come back to that. Yeah. So all these pictures here certainly are didactic. They are simplified. Yeah. Anyways, we are in a single row vibrational quantum state. Yeah. It's highly excited. It's usually the -1 state. Not quite sometimes, yeah, but it's effectively the last bound state. We count them from threshold. Rotationally, they're usually very cold. Yeah, they are typically they're S or perhaps P or D, depends a bit on what you're doing, but they are rotationally very cold. And all this has been demonstrated. So when I say BB is Bose-Bose or Fermi-Fermi or Bose-Fermi, different ones, you can actually create all kinds of end-over-end angular momentum for the molecule, yeah. And they are the binding energy is very little, kilohertz, megahertz, and perhaps then gigahertz, yeah, if you go further. And you can use further avoided crossings to take your molecules to lower lying states, but it's still a very weakly bound Flashback or van der Waals molecule, yeah, for all practical processes, yeah. So what are the relevant processes that these molecules are subject to? That's actually collisions, yeah. So atom-molecule collisions play a role while we create the molecules initially, because there's still atoms around, and when we then have a molecular sample, we have to worry about molecule-molecule collisions. And when I say worry, actually, that's what we want. We want interactions, yeah, because we want to create an interacting gas in the end, yeah. So, but the first problem that arises from collisions is that collisions lead to relaxation, yeah? So molecules collide and relax into a lower lying state. And in fact, I'm pretty sure that Johannes Hecker-Deinschlag will talk about this later in this workshop, yeah? So you have here in my comic, a collision between an atom and a molecule, and that will release a significant part of the binding energy. Usually the decay is not into the very ground state, but it's actually a decay in one of the nearby levels. I think the argument is basically a Frank Condon type overlap argument. Yeah, so you create still a molecule that's still very weakly bound, but you remove a few megahertz of binding energy or gigahertz, and that's already enough to kick out these molecules from our trap. Yeah. Our traps have tens of kilohertz binding energies typically, yeah. So actually seeing this was the first publication on this loss. I should mention that was from the MIT group of Wolfgang Kerterle, seeing loss of molecules in the trap, and I just want to give this as a reference, yeah. I have to say, certainly we saw this also very quickly in our experiments, yeah. And so Wolfgang Kerterle documented the molecule loss and the atom molecule loss in his trap. So why is this relevant? Because let me come back to the creation. When you create the molecules, we have to go adiabatically across the resonance. So we cannot do this at infinite speed. There's some time scale associated with that. And so there is time for the molecules to collide, the newly formed molecules to collide with the atoms then, right? So that's actually the problem. And so either you make sure that you don't have any other atoms around anymore, yeah? So the ideal situation is where you just have 2 atoms per site, and per well, per trap, and then there is nothing else to collide with, yeah? So that's the idea, yeah? So that limits the lifetime, and if you have more than 1 atom at any well in your trap, yeah? So an obvious solution is use an optical lattice, yeah? So trap your molecules inside a situation where you can localize the atoms and make sure that you only have few atoms per lattice site, ideally exactly 2 atoms per lattice site. Okay, and then you end up with 1 molecule per lattice site after doing the process, yeah. So this is in fact what I already told you. I'm just coming back to this comic of mine from earlier where we mix and we create atom pairs in this lattice as indicated here in step 2, yeah. So and only then we create the molecule. So this step now then from 2 to 3 is the one that I just discussed, and that should work well. So now let me come to step 3 to 4, yeah. So this ground state transfer, yeah. So this should be briefly mentioned because it's important for everything, yeah. You saw this picture here already earlier. This is the case of rubidium cesium again. I'm not detailing exactly this initial state here. Yeah, I don't have the time, this specific hyperfine state here. I'm not showing any details here. But basically, we are lucky. This is essentially a 3-level system, perhaps with some spectator levels, in particular up here. And one can be lucky or unlucky. I think we've been lucky with this choice of our states. And so how does this work? And let me just remind you of your basic atomic physics. If you have 3 levels, there's 3 levels with 2 lasers on resonance. And that's actually only what you need. You can immediately write down the matrix, the 3x3 matrix, and you will immediately find that one of the solutions, the eigenstates of that problem actually has this form. It's a dark state because it does not involve the excited state. Yeah, so we assume the excited state has some loss rate gamma that is non-negligible. Yeah, that so we want to avoid that excited state, and the solution is this interesting combination between the 2 ground states. Yeah, this coherent superposition. And I think if you've never seen it, I think it's almost evident that with 2 lasers on resonance, you create this kind of superposition state. Yeah. And if you want to learn more, this is a good review from Nikolai Vitanov. So omega are the Rabi frequencies, the coupling strengths on this transition. And as you know, it's a product of the dipole moment and the electrical field. And I don't go into any of the details, but in fact, the problem with molecules is, if I go back here, you have to obey the Frank Condon principle. So these dipole moments are rather weak. Yeah. So that actually is important to know. Yeah. So these Rabi frequencies are not that strong in view of the fact that these dipole moments are not infinite. Yeah, and they are not atomic. And they are strongly suppressed because of the overlap of the nuclear wave functions. So and also you cannot crank up the electrical field too much, because at some point you run into other problems like Stark shifts and so on. Yeah, so there's a compromise at some point what you want here, but it turns out it works all nicely. Yeah, so rotating now from the initial state 1 into the final state 3, in view of this interesting superposition here, will require you to turn on the second laser first and the first laser then afterwards. So explicitly, this is no pump dump scheme, but it's really a coherent transfer from 1 to 3 with this counterintuitive pulse sequence. Yeah, so you have to have a sizable overlap of these 2 light pulses. Yeah, I don't go into the details here now, but basically what happens is that laser 2 creates an outer town splitting, and then omega 1 mixes in these states and then rotates the state from 1 to 3. Then when you do this, populations will change as indicated here in this comic. I'm going to show you data in a second, from 1 to 3. And this is all well known. It's been used in molecular spectroscopy, usually by going the other way around, going from ground state molecules, but without any rotational control, for example, in a molecular beam, to go into more excited states. We are doing this now the other way around, and using it for full state control. And also for the young students, when I proposed this long time ago, an eminent physicist that came to our lab said, not gonna work. Okay, well, it works, yeah. So, okay, the person was right to some extent because there were things to watch, yeah. Because as I said, the overlap integrals are small, and so it's for sure not easy. But in the regime that we work, it actually works really nicely. So, but nothing comes for free, and that's actually one has to be adiabatic, and adiabatic actually means in this particular case that the product of the time over which you do it times the Rabi frequency squared has to be significantly larger than the decay rate. It turns out one can fulfill this, yeah, in view of the fact that usually these excited states, these mixed states, are rather long-lived, yeah, and then this actually can be fulfilled, yeah. And it turns out this 2 pi squared factor is actually there, yeah, and you want this factor to be this on the left by a factor of 10 larger than the right, roughly, yeah. So then this factor 2 pi actually squared does play a role, yeah. So anyways, yeah, I think there's a question already in the chat, but let me see, let me just show you how this works, and then I take questions. I'm happy to take a few questions. So what you do in the experiment, you actually, I go back, you go from 1 to 3, and then you go back for detection, and then you do everything reverse, yeah? So that's the idea, yeah? So we, here on the left, you create the ground state molecules, on the right, you go back, and then you dissociate and image atoms, and we detect these Flashback molecules as I just told you before, yeah? So this works actually really nicely, and as you will see, creation happens on 10 microseconds, detection happens here within tens of microseconds, and the waiting time can be seconds, yeah? So, go down, go up, that's what I just said. And okay, perhaps, but before I show you some experiments and data, I'd have a look at the chat.
So there is one question.
Yeah, I read the question. Yeah. So certainly,
okay.
Yeah, the phase coherence between the two lasers is crucial. Yeah. So while you do this, while you do the transfer, let me you see now it's jammed. When you do this, the two lasers have to be phase coherent. Yeah. So in fact, what we do is we make them stable passively a lot. So while we do the transfer, they are very stable. It doesn't matter from shot to shot. Next time there's a totally new phase, but the difference phase has to be stable while you do this. If it's not, it will actually rotate you out of this dark state and destroy your dark state. Yeah. So this is actually crucial. So you need to do some tricks. You need to lock lasers very well to a high finesse cavity and so on. Yeah. And in particular, if you want to play with a longer time scale here for being more adiabatic, you need longer coherence times. Yeah. So perhaps I say this already at this point. The limits of this have not been tested, I have to say. We see efficiencies in these experiments of 90%. The question is, why not 99%? Well, I think the main reason is because nobody has pushed for it yet. But it's then very stable lasers. So here's a gallery of experiments that have been done since 2007. Actually, it started here in Innsbruck with 2 endeavors on rubidium and cesium. At the same time, our friends at GILA worked on KRB. And then in 2008, we could actually demonstrate that we can do a transfer actually into a chemically bound state. Yeah. So when we actually showed this, it was clear to me this is going to work, because the second step is not so difficult. It's actually the first step from the weakly bound level to that step. So that was for us the important experiment to demonstrate that this is possible. And that's actually where this colleague said, no, it's not going to work. Yeah, because the step from 0 to 73, let's say, that was demonstrated before the other way around on other molecules. We were confident that this worked. Yeah. Okay, so we could then already produce quite dense samples of molecules. And a little later, our friends in GILA demonstrated transfer to all the way to the ground state with a binding energy of 120 terahertz, half an electron volt, roughly. Yeah. So in 2008. So this shows data for the case of rubidium cesium for a sample that is not super cold. It's hundreds of nanokelvin trapped in a lattice, though. after production, but not with full control, not in the lowest band of the lattice. The single pass efficiency here is usually on the order of 85 to 90%. And this is the publication down here where we demonstrated that. This was done on a sample where the filling fraction in the lattice was 2 or 3% or so. Yeah, so rather low. And okay, but and the holding time is rather short. Here is just 15 or 20 microseconds. Okay, so this is the situation for rubidium cesium. Yeah, so now I still have to tell you how to produce the pairs up here. And I see there's another question in the chat. Let me see. Yeah. So the question is it possible to bypass the step of magnetic Flashback isolation and to do stirrup from atoms to molecules directly? Yes, this is actually, there have been demonstrations of this. Actually, one of the Japanese group has been working on this, and the efficiency is okay, but not very high. So it turns out I think if you want to push this towards really high efficiencies, we probably have to do it via the Flashback step. Yeah, I mean the advantage of doing Flashback, the optical transfer from the Flashback situation is that the Frank Condon elements already are much better. Yeah, so that's what we found, and that's what I think still needs to be demonstrated that this works otherwise. Yeah, with similar efficiencies. Okay, so okay, this is back to my comic now. Okay, when I actually call this, I have to. So it turns out this mixing is difficult. So let me do a quick diversion and tell you how we did this with a single species first. Yeah, so homonuclear. Yeah, and actually, so how do we create atom pairs with a homonuclear system? And that turns out to be rather easy. You actually take your BEC and turn it into an insulating state when you go to the superfluid to insulating transition. And I have no details on this transition here, and I think our colleagues, Emanuel Bloch and others, will talk about this a bit in this lecture. So I actually decided to skip this. Just for you to remember, what we use this as a tool. Yeah, so we use it as a tool to prepare the so-called 2-atom mod shell with a quite high probability. So the center part of our trap, typically it's 50,000 particles that are actually at doubly occupied sites. So to give you numbers, I haven't written down any numbers here. We have a BEC of 100,000 atoms. We are able to turn 50,000 of these into pairs. That's the limit that you get, basically the limit that you get from harmonic trapping. If you had box trapping, this would be different, would be higher. So the 2-atom mod shell contains 50,000 atoms. That means we have 25,000 molecules at maximum. Yeah, and when we do it in this way, and I will not tell you, you can do it in another way and even more efficiently. But with the 2-atom mod shell, we get about, well, for sure 20,000 molecules. Yeah, in the lattice, and these we then turn into the weakly bound molecules. Also here, I won't show you exactly the details how we do this. I showed you the schematics, but not the specific states. And then this ground state transfer efficiency is, in this particular case, for homonuclear cesium is 80%. Not 90%, but 80%. Why is it 80%? Because it turns out it is a 4-photon process. Homonuclear cesium is not the way the molecular potentials overlap, bottom and top. It turns out that a single 2-photon stirrup step will not work. Actually, we played around with this, no chance, but we need a 4-photon stirrup. So we actually set up 4 lasers that were all phase coherent to go all the way to the ground state. And this is the schematic. So it's not a 3-level system, it's a 5-level system from the initial state, which is basically from, if you count from below, it's the 155th vibrational state all the way to the ground state. Yeah, and this is the scheme of doing transfer 1-step, 2-step, back and back. Yeah, as this is generalization of what I just showed you. So I see again for questions in the chat. Yeah. So so okay. Yeah. So NACS is done in a single atom tweezer trap. Yeah, so the Harvard experiments, yeah, are done with single molecules in tweezers. That's certainly a different situation because, well, in the end, we are interested in really in the many-body system. With tweezers, you can perhaps eventually take it into a many-body regime, yeah, but that still has to be demonstrated. Okay, so that was this question. So this shows the transfer from the initial state to the ground state for homonuclear cesium. This shows the intermediate transfer step here with a an efficiency of more than 75%. When optimizing everything, we were actually able to demonstrate an efficiency of 80%. And this is while all other lasers are on resonance, the fourth laser is being detuned, and this is the efficiency. Yeah, so about 80%. So each step being about 90%. So there are and I actually indicated that earlier here, there are some defects, yeah? So this red molecule here is a molecule in the wrong state or actually something that got lost on the way, yeah? So it's actually not totally clear where this molecule is lost, into what it is lost. We don't know, yeah? One can make guesses. So 80%, but that's actually quite a dense sample, yeah? 80% at very low temperatures. And talking about temperatures, this is an image of a band mapping image with where we exaggerate the color scale, and this shows the lowest Brillouin zone of our lattice, and you see that essentially all the molecules are in the lowest band. So we don't excite the molecules to higher states in the trap, in the band, and so in the lattice. Yeah, so that's actually quite important to know, and it could have been different. Yeah, because I haven't said that. You want the initial state to be trapped and also the final state to be trapped. It turns out we have fortuitous at the trapping wavelengths that we are using. The initial trapping and the final trapping are almost identical, just by accident. Yeah. When I talked to the funding agencies, I said, well, I computed it and I knew that it would work, but actually, admittedly, it was an accident, and we're lucky. And it turns out, also for KRB and some other molecules, we are near this sort of magic wavelength where trapping in the initial state and the final state is almost identical. And we, if it were not, you would actually do motional excitation of the molecules, yeah, in the lattice. Okay. Talking about lifetime, yeah, this is an image of a long time ago of molecules trapped in the lattice in the lowest band. The lattice is at 1064. It's rather far detuned from the relevant excited states. The lifetime is 8 seconds. Yeah, so that's actually long for anything we ever want to do, and I'm sure it could be optimized. But it shows that these molecules, when they are left alone, sitting at the individual wells of the lattice, not doing anything. Yeah. Now, I'm showing you actually this to show you now what happens if you let the molecules interact. Yeah. So this brings me to the question of stability. Yeah. So collisions, two-body collisions, or perhaps effective three-body collisions. And this now shows data where we release the molecules, as indicated here, into stack of pancake traps. Yeah, so we have the molecules in this vertical lattice. At the end, after we remove the lattice beams from the horizontal directions, and the molecules live in traps that are 2D. Yeah, so they collide in 2D. And what we see is that we have now a lifetime. If you fit a 1/E, but it doesn't fit at all, it's actually that lifetime is on the order of 10 milliseconds. So before it was almost 10 seconds, now it's 10 milliseconds. So letting the molecules collide decreases the lifetime by 3 orders of magnitude. Yeah. So what I'm showing you here, this is the molecule number as a function of hold time. Now it's not seconds, but milliseconds. This is logarithmic. And the gray dots are data, our molecules in the trap. So initially we have about 20,000 molecules. And then after 80 milliseconds, we have 2,000 molecules left over. And the lines that I'm showing are fits, yeah, in some theory. So actually the red line is a two-body fit, actually for the entire range. It doesn't work, yeah, it doesn't fit. And I have to say, certainly we require the two-body fit to to agree with our initial data. Yeah, that's a constraint you can easily do. And so you see it doesn't work. Two-body fit doesn't work. It works initially quite well, but it doesn't work over the entire range, over these 80 milliseconds. We can do a two-body fit on the first 10 milliseconds, then it works even better in the first 10 milliseconds. Certainly it doesn't work as well back here. But this tells us it's a two-body process initially, yeah. And the dash color lines actually assume that we have something complicated going on that I will explain to you in a second, namely the formation of complexes. Yeah, with some one free parameter. I will show you that in a second. Sort of free parameter. Yeah. So the upshot of all this is what we measured is that the initial decay is two-body. It's not one-body and it's not three-body. Yeah. So it's molecular two-body collisions. Yeah, quite interesting. So what's happening? And this is summarized here. This is what John Bone proposed nearly 10 years ago. That if you have two molecules colliding, they can actually form a complex. Yeah, even though we have them in the very lowest state, they cannot relax in any way. They cannot form a trimer. They cannot form a four-atom molecule. Yeah, but transiently they can go into this four-atom state, and they can break up again into this into these initial dimers. But what they can also, if the lifetime of this complex is long enough, it actually can collide in a three-body type with another molecule, and that can lead to loss from the trap. So the formation is two-body, but the loss is three-body. So this turns actually into a difficult experiment, and the rate equations on the next slide. First, we have three parameters: the complex formation rate, the dimer complex fission rate, and the lifetime of this molecule that breaks up again into these complexes. And that's actually the model here for the number of molecules and for the number of complexes, where, let me walk you through this, where you have a rate of complex formation, where you have a rate of complex breakup, and where you have a rate of complex relaxation with another molecule. That's the only thing that's around, a molecule. Yeah, it's a pure sample of molecules. Yeah, that's the rate for, that's the number for the molecules, and that's the number of complexes in the same way. Yeah, so that's a simple model, not assuming any temperature dependence and so on. This is in effect done in the zero temperature limits anyways. Yeah, so temperature effects will probably not play a role, that's the simplest model you can set up. Yeah, and now what you can do is you can see we can measure alpha. Yeah, that's what I just showed you. Yeah, alpha we can fix from these measurements immediately because that's the initial decay. What we don't know is these other two parameters, gamma and kappa. Yeah, so we can do those something. Our molecular friends tell us that they actually know kappa. They can actually calculate universal kappa from van der Waals theory. So they can actually give us a number here. And when we fix that, we can get that gamma, yeah, or 1 over the lifetime. So gamma is this lifetime of this molecule complex, yeah, tau. And this is actually shown here in this plot. This is again the data. And I'm plotting now the curves that all fit our data for 3 possibilities of this kappa, where we have a universal kappa from van der Waals theory. I'm not detailing it at all here. We have 10% of that, or we have 10 times that value. And choosing that, we can get the dash curves here are number of complexes that we then have in the system. Yeah, and that actually is sizable. Yeah, in particular for this value. Yeah. Anyways, this fits the data very long. Now, with these 3 numbers, you can get these lifetimes, and you see the lifetimes. Even that lifetime here, 4 milliseconds, is very, very long. So these molecules come together and stick together for 4 milliseconds, and this here is actually infinite. Yeah, 300 milliseconds, I would say, for a collisional process. Yeah, so that's actually quite amazing. And and then the question is, what's happening there? Yeah. So our data is consistent with this model, but I have to tell you, long story, we've never published this. This is a nice data where we decided never to publish it because we were not sure whether there's something else. Yeah, okay, we could publish and say, well, that's what we see. But I'm a person who always wants to understand everything. Perhaps one shouldn't have that attitude. So in particular, there's now a discussion in the literature whether there's photochemistry going on while these collisions happen. And there's some data that supports that claim and some data that does not support that claim. Anyways, yeah, so I close this chapter and I come back to rubidium cesium. Okay, I see a question in the chat.
Yes.
Let me see. Open it. Why does it not open? Chat, it opens.
So maybe I can read it. So is interaction among the molecules in the lattice affect the stability?
So, in the lattice, when they are actually not allowed to collide because the lattice is too deep, yeah, then nothing happens. Yeah, so the molecules live very long. So we don't think this interactions play a role when we actually have the lattice on. But when we allow them to move in 2D or in 1D, I haven't shown that. We've done also experiments in 1D, and one can but then the analysis gets a bit more complicated because in 1D hell breaks loose because of the confinement. Yeah. So anyways, but we have a lot of on that, and but we see also we see very strong loss immediately, and it has to be due to interactions. Yeah, unfortunately for the molecules, we cannot turn off interactions by some other mean. We can only turn off interactions by adding potentials. Yeah. Okay, now let me come back. So how am I doing in time? I have to watch a little bit time. I started when
about 30 minutes. You started at 15 plus 4, so you have around 30 minutes or so.
30 minutes or so. Okay, then I'm doing fine time, I think. Yeah. So let me go back to rubidium cesium, yeah, where we want to create these atom pairs initially, yeah, and this mod insulator with 2 different atoms of each type at each site. Yeah, and then go through this route as I indicated earlier. Yeah, so this we discussed now, Flashback association, the stirrup transfer we discussed, and it can be done better, but I think it's very well understood or good enough for practical purposes. And then this initial step. Yeah, and in fact, the Giller group 5 years ago published a paper on mixing a mod insulator and a band insulator, and in our case, we find that this is in fact the bottleneck. So perhaps with fermions it's a bit easier, yeah, because as I mentioned earlier, so this is the bottleneck. So creating atom pairs is the difficulty. And so let me take you to the next comic. So the idea is to start with a single atom mod insulator state. Yeah, so this we know to do how to do very well in our lab. In one of our machines, we do this essentially every day, and we can localize 90% of the cesium atoms from the BEC in this way. Yeah, so this superfluid turns into almost perfectly into this one atom mod shell, and actually cannot turn 100% into that because you have the superfluid fringes outside. Yeah, so we are close to the maximum here. And then the idea is to bring in the rubidium BEC from the side. Yeah, initially separated actually, as I will show you in a second. Yeah, and then to bring in the rubidium in some way and to raise the lattice further and to go through the phase transition to localize rubidium one more time, as indicated here. Yeah. So what we want to do is we want to allow one rubidium atom into these sites, but not a second one. Yeah, because that's detrimental. Yeah. So that leads to 3-body loss, and in view of Efimov states and strong 3-body collisions, we don't want that. Yeah. So this process should not happen. But the question is, how does the first rubidium enter on the site where you already have a cesium atom? So if you think about this, we need to do something about it. It doesn't do this on its own, yeah? And we want to prevent the second rubidium atom to come in. First of all, you need interaction control for that, yeah? And the tool is now an interspecies Flashback resonance between rubidium and cesium. So this is the situation, again, of Flashback resonances. I think I can flash this quickly. The generic picture of a 0 crossing in the vicinity of a Flashback resonance here, yeah? And then we want to populate this bound state on the resonance. So what we need is actually, we need both. We need the 0 crossing and the bound state that pops up at threshold. Yeah, so that's what we'll be making use of. and explicitly say this is important for us, the zero crossing. So this is now the real situation. This is the theory result from a lot of measurements that we did long time ago, and we got a lot of support here from, in particular, Svetlana Kotochigova from Temple University to identify all the resonances and the bound states as indicated here. So this is the zoo of bound states. Well, it looks bad, but it's not so bad. It's all, you see the magnetic field. We control our magnetic field at the level of milligauss, and so we can address each of these resonances certainly individually. The resonance of our choice is the broadest one here at around 350 Gauss. I'm zooming in. This particular one here, that's the one, and the bound states below. Yeah, these are the ones of our interest. Yeah, so near this resonance, we have also the zero crossing. Yeah, I'll zoom in a second. And the slope at that zero crossing. Yeah, and let me go back. What's also important for an experiment is how gentle this slope is. Yeah, it should not be too steep, because if you have magnetic field fluctuations in the lab, which you can never avoid, you will wiggle around too much here. So the zero crossing is sufficiently gentle, so it's usable. Yeah, it has this slope of 3 Bohr radii per 10 milligauss, and that's reasonable. So having said that, what about the other interactions? Yeah, so we have now, this is rubidium cesium. This shows the scattering length of rubidium cesium in specific spin states. I haven't detailed that, but it's the very ground states, hyperfine ground states for both of them. What about rubidium and cesium? Yeah, there are 3 parameters, but only 1 knob to turn. Yeah, just remember that. We have only 1 magnetic field, and it's difficult to do anything else. Yeah, so rubidium is not a problem. It has 100 Bohr radii and also almost no loss. Yeah, so rubidium is easy cheesy. Cesium is potentially the problem. And if I go back to that value, 350 Gauss, that's actually where cesium has, and I showed you this picture earlier, or similar one, where the scattering length is on the order of 2000 Bohr radii. Yeah, so this shows the scattering length for cesium, the lowest hyperfine state specifically of cesium as a function of a magnetic field. You see these 3 wonderful resonances. In fact, this resonance here at 800 Gauss is the widest resonance in the field as far as we know. Yeah, the widest Feshbach resonance. And but we sit here at on this slope here at 350 Gauss. So cesium scattering is very strong, and at 2000 radii positive, but you still expect the 3-body loss rates to be very large. So without showing you details, I'm just showing you the data. This is the lifetime of cesium atoms in a mod insulator state. So in a state like this, yeah. Sorry, something popped up. So in a state like this, the top one here, yeah, 1 atom per site, yeah. And the lifetime as a function of lattice depth. Yeah, so actually we go through the phase transition around 16 recoil depths. So this is a typical unit for the depth of the lattice. If you're not familiar with this, don't mind. This is the horizontal scale is just depth of the lattice. Here is the phase transition, and we are deep in the insulating regime. The lifetime is not 10 seconds, it's 2 seconds. Yeah, okay. We don't know why. It's finite, yeah, but it's actually good enough for all practical purposes, and it's actually our it's ongoing work to understand what's going on there. If you go away from that lattice depth, you will get very short lifetimes. Yeah, here hundreds of milliseconds or even below 100 milliseconds. Yeah, so the preparation is certainly, we do the preparation for the sample at low fields. Yeah, actually we prepare the sample around 20 Gauss down here, and then we ramp the field to 350 Gauss. Okay, so that's finite, but okay, yeah. So how do we do the experiment now? We have a lattice setting with 2 samples, rubidium and cesium, and let me even simplify that setting here. We have 60 laser beams going into this chamber for everything, for molecular control, imaging, laser cooling, advanced laser cooling, additional laser cooling, and so on. So I'm totally simplifying it now to only the lasers that we are using for the trapping and for the lattice on top. So the lattice is actually very big. It almost doesn't do any trapping. It's indicated here by these pancakes, top and bottom, left and right, a cubic lattice. So let me even simplify that. So we have these two superfluids. We turn the right one, cesium, into this mod insulator state, and then move our superfluid rubidium on top of cesium. I have to say something about that. And then we create this, our attempt to create this double mod insulator state. So what does that need? It needs two things. It needs superfluid transport. So to give you a feeling, this goes across about 100 microns, so 200 lattice because each lattice is half a micron away roughly. That's one thing, the superfluid transport. And what we need is interaction control as when the two samples meet. Yeah, and that is now shown in a moment in this data. But let me just tell you quickly how we detect. Yeah, well, detection, we go back to atoms and we detect atoms separately from molecule for cesium and rubidium via this Flashback trick. Yeah. So this is now the specific molecular level scheme. So this shows binding energy of the most weakly bound states as a function of magnetic field around this resonance region that I just talked about. Here is the entrance door that I've talked about, where we take the atom pairs into a very weakly bound molecule, this state below threshold, and then the state actually on an avoided crossing turns over. So there are some states that I have not labeled. Actually, I have not labeled any of the states because it's not relevant here. And only one state I should highlight, there's a very weakly coupled state here near the resonance. Yeah, the resonance is actually caused by this avoided crossing here on below threshold, pushing this green line through threshold. That's the relevant state. And there's another weakly coupled state. It turns out this is sufficiently weakly coupled that it doesn't hurt us, but it's there. Yeah. So that's the route from atom pair to molecule with a binding energy of a few megahertz in the end. And this is now how the experiment works. Yeah, we move here. We show the overlap of the two samples, and we show how efficiently we produce these Flashback molecules. Yeah. So on the left, it's absolute numbers. On the right, it's normalized to the number of the atoms in the cesium BEC. And since we know we turn 90% of the cesium BEC into lattice, this gives us approximately an estimate for the filling, for the fractional filling, actually a lower bound, in fact. Yeah. So this is as a horizontal lattice position. Yeah. So you see we have sort of a top hat overlap because we have these two samples that then merge, and then when we go beyond that, we actually, the overlap is not as good anymore, spatial overlap, and you see what the size is. Yeah, so we have to control this at the level of micrometers. This is horizontal overlap, and this is vertical overlap. So we have to make sure we really bring these samples on top of each other at the level of a micron. And this is now crucial. This only works. So we optimize the spatial overlap, but it only works well if we null the interspecies interaction, the rubidium-cesium scattering length. And this shows the same data now as a function of interaction strength, number of molecules on the left, lattice filling fraction on the right, as a function or lower bound for that. Yeah, it's slightly higher probably as a function of the interaction strength. And we see that we can we obtain a maximum here at the value that's consistent with 0, yeah, within our error bounds. Okay, so this is how we do this. Yeah, so we have about 5,000 to 6,000 of these molecules when we overlap the two samples in the lattice, and the lattice filling fraction at the center of this trap is on the order of 30%, perhaps a bit better, but it's not unity yet. Yeah. So what is the main enemy? Yeah. What is the main enemy? In fact, let me go back quickly to that. It's when we overlap the two samples, when we actually, let me see this plot. This plot here, yeah. So when we bring in the superfluid rubidium is superfluid, yeah. It's not yet localized. Certainly, we don't want it to localize initially, and there's a certain probability, Poissonian probability, that we have not just one rubidium atom at a site, but two. yeah, or 3 even, yeah. So that's non-zero. So we have a certain probability that that we bring in more than one rubidium atom, yeah. That's one enemy or one problem, yeah. It actually turns out that the lifetime of the cesium mod insulator already is a problem. As I said earlier, it works, but it works only so-so. So we see that while we bring rubidium on top of cesium, while we do the dynamical process, we already lose cesium. Cesium hasn't seen rubidium yet, but it's still, we already lose it, yeah. So that's also one problem, yeah. So that this lifetime is not finite, yeah. And then we do this overlap, and I don't show you data for this, yeah. I actually didn't bring it, yeah. The question is, when I go to this comic, how quick can you do this? What I've called superfluid transport, yeah. So this blue arrow here, so you have a superfluid here, and how quickly can you move this? And there's actually a speed limit. And we see the speed limit, yeah, we actually have to be significantly below the speed limit, because it turns out if the sample is not superfluid anymore, when we go over here, we don't create any molecules. So it turns out the fraction of molecules is directly related to how what the BEC fraction of that rubidium BEC is. So it's strongly related to that. So we have to watch it. So as we move the sample from left to right, we have to make sure that it stays a superfluid. And in fact, we were not sure whether this would work at all, because I'm not aware of anybody in the literature moving any superfluid through a lattice across 200 lattice sites. Yeah, so this is actually brutal. We have what we do is we move the underlying dipole trap, as indicated here, and move it just across. Yeah, and so you see everything warps as you do this, and it could break loose. It turns out it works pretty well. Yeah, but the details of that have to be still sorted out. So actually, we have not identified a single reason, but it's, I think, a multiple of reasons that can be optimized. Yeah. Okay, so then perhaps I stay with this comic, because I haven't brought any other picture for that. You could do this in a different way. You could actually merge two samples, rubidium, cesium, that are not initially side by side. Here they are next to each other, yeah, really horizontally at the same level, and we just move them we move the rubidium sample from left to right. You could actually move them up and down with sort of pancake traps. So you have two samples that are 2D at the outset already, and then you just merge, do this merging along the tightly confining direction, along the pancake direction, the tightly confining direction in a pancake. So in this, if you were to do this, so you prepared cesium in a 2D situation, rubidium in a 2D situation. And in fact, we'll see that later, our quantum gas microscope people know to do this really well. Just one layer of rubidium atoms, let's say. And then to merge that one layer in 2D layer with the 2D cesium layer. And then actually the merging would be only 2-body, and you would not have the problem of any 3-body processes. Yeah. So you would, in this sense, not move a superfluid through the lattice, but you just would move two mod insulators on top of each other by removing a barrier in between. Yeah, I think those of you who know a bit about lattice physics can immediately visualize how that can be done. Yeah. So that's actually the goal of all these endeavors at some point, because for a lot of these experiments, we are totally happy with 2-dimensional dipolar molecular samples. Okay, so let me see.
There is one question. Would you like to take now?
Yeah, I can take questions. I'm actually almost at the end. I think I've rushed a little bit. Yeah, yeah. I'll take questions in a second. Let me just summarize perhaps this part. Yeah.
Okay.
So this rubidium transfer, this is 2-photon process. It's very efficient. The lattice filling is decent. Yeah, it's not yet where we want to be, but it's decent. The efficiency for cesium homonuclear is also decent. I think it can be pushed, and we actually know what our lasers need to have more phase coherence. Yeah, that we know. This sentence here is a little bit at the moment perhaps challenged by the results that I'm citing down here. I think we used to have the coldest molecular samples in Innsbruck, but I think the GILA people have beaten us now, yeah. But I left the sentence because a little provocative, yeah. Rubidium KRB is doing really well, as you will hear from Junyi. He can take his gas of KRB molecules into Fermi degeneracy, yeah, at temperatures significantly below a microkelvin. I forgot what exactly his Fermi temperature is, but it's on the order of 100 nanokelvin. So, and you, well, stay tuned. This is a really nice result from last year. And in fact, certainly in Innsbruck, we want to do the same with our bosonic systems for rubidium cesium and for potassium cesium in a similar way, but well, similar meaning into a similar regime, but with the techniques that I've discussed so far. Okay, let me take questions at this point. Okay, I can read it. And the first question is: are we able to handle each atom in the two atom site, or is it considered as a molecule and handled together? So yeah, so perhaps just initially we localize two atoms at a lattice site, and then we turn that atom into that atom pair into a molecule. So certainly the question is when there's an atom pair and when there's a molecule, what trap frequency, for example, do they see? Is there any excitation as you go from the two atom state into a molecular state? And it turns out no, because the atoms, they have the molecules have twice the mass, but they also have twice the polarizability, the AC polarizability. So we don't see any excitations as we go from the two atom state to the molecular state in the lattice. So the next question is, can it possible to have two atoms superfluid in one place? Yeah, that's what we actually, I think the question aims at what we did with cesium. Yeah, let me actually go back quickly. So with cesium, I'm going in the wrong direction. With cesium in this picture here, my comic, yeah, we work just on homonuclear cesium. Actually, we have initially a superfluid of cesium, where the chemical potential is such that we will actually preferentially fill the two atom mod shell as we raise the lattice. Yeah, so this is so basically what we do with the underlying dipole trap, weak dipole trap, we set the density such that we fill up the two atom shell maximally, but not the three atom shell. Yeah, and then it turns out that about 50% of the atoms sit in the two atom mod shell and 50% sit in the one atom mod shell. Actually, my comic here is not quite correct because it should be 50-50. Yeah, so but the set part is a superfluid with sufficiently high density that you create atom pairs in the lattice. Okay, so that's one question. Perhaps I answered that. Yeah, but I'm happy to take further questions. So next question, let me see.
What aspects of phase-back
association helps to improve the phase-space density as compared to photo association? Well, Flashback association, in particular when you do it in a lattice, is actually very efficient. Yeah, so doing this step from here to here is 90% efficient. Yeah. So and we what we actually do when we create from the atom pair we create the molecule, we already reduce the internuclear distance by a lot. And in fact, it turns out, I didn't show that and I didn't bring any slides. When you go via avoided crossings to even further more deeply bound states, you even reduce the internuclear distance even more. So these molecules are already fairly tightly bound. I mean, they're still van der Waals molecules, and they have a much better Frank-Condon overlap with the excited states that you need for the stirrup transfer. So that for sure helps a lot. Yeah. And in fact, as I said earlier, we found this by accident. Yeah. We found that our Flashback molecules are susceptible to multi-frequency light, and they were not susceptible to single frequency light. And that so we saw that the Flashback molecule we can much more easily drive optical transition on the Flashback molecules. So I think this was this question. Let me see the next question.
Could you elaborate more about experimental
method of merging two 2D lattices along the tightly confining direction? Yeah, I think for this, I mean, it hasn't been demonstrated certainly, but I think what we do is we prepare separately two-dimensional condensates with the way how you do it is you start with your 3D condensate, but then you load into light sheet traps, the traps that you generate by focusing a beam very tightly along this horizontal direction. So the focus is along the vertical direction, so that it's a horizontal light sheet, and then you load your initial 3D condensate adiabatically into this 2D plane. That I think we know how to do. The community for sure knows how to do it. And you have to do this though for two samples, yeah? Top and bottom, rubidium and cesium. And I think that can be done. I don't see any problems with this. And then certainly you have to overlap everything with the lattice. And then you have to keep in mind, you have to have a lattice also in the vertical direction and take away the barrier between the two samples. And that also in principle has been demonstrated by actually doing this in a super lattice type fashion, where you have two different frequencies in the lattice, where you have a barrier in first, and then you remove the barrier by removing the higher frequency components in your super lattice. That in principle can also be done. But as far as I know, it's not been demonstrated, yeah. But we are working hard on this, yeah. So to do this with rubidium cesium, and in particular with KCS. But we'll see. I mean, we have to marry all this, combine all this with electrical field control plus high resolution imaging. So in fact, we are working right now on designing a chamber where we have everything, yeah. Lots of beams coming in, electrical field control, Faraday caging to avoid fields from charging up lenses or vacuum components, windows also. In fact, Jun Yi will tell you how they do it, and we are working on something similar, but with hopefully with a bit better resolution. What he has in his chamber, he has two plates, transparent plates, but they are coated so that they are electrically conductive. And so he can put voltages on these transparent electrodes. It's Indian tin oxide, ITO it's called. And these ITO coated glass plates are the top and bottom electrodes, apart from other electrodes that he has in the chamber. And that has to be all combined with the short working distance of your lens for imaging, plus the capability to create very deep lattices for imaging purposes. If you want to image individual atoms later on, so you do all that entire procedure, and then you want to image these atoms individually, then you need to raise your lattice by a factor of 100 or perhaps even a factor of 1,000. I think 100 is okay with proper laser cooling, and then image. And so you need to also be able to have high light powers inside your chamber while you then image, yeah. So I think that perhaps answered that question to some extent, yeah.
There's one more question.
So there's once having 2 atoms per side. What is further trying to do with these lattices? So I mean, the application of 2 atoms per side, our primary application is turning these 2 atoms in the lattice into molecules. Yeah, so the goal is really to make these molecules. I hope I understand your question right. When we have other endeavors in our group, in fact, there's a publication from late last year that we finalized after many years of work on not molecules in the lattice, but doublons, atom pairs, move through the lattice together, even though they are not bound as a molecule. You can do this with atom pairs that interact repulsively or attractively, and we call them doublons. And we actually, it turns out the theory has a hard time modeling our system. Yeah, we have very good control by now, and it's hard to model the processes that actually happen. So the goal of these two atom doublon systems is to create novel superfluids. There are proposals in the literature to create novel types of superfluids with atom pairs in lattices, bosonic atom pairs, actually, not fermions. Yeah, bosonic atom pairs, and well, actually, at the moment we are not doing this because of lack of time and manpower and human power. But it's an interesting avenue on its own. Yeah, I don't have any slides on that, unfortunately, to detail more on that. Yeah. Okay, and certainly I invite everybody, just send me an email, just write, I was a member of the school, and I will immediately answer you any questions that you might send me via email. Yeah, I'm very happy to do so. So let me actually then, actually with these questions, I'm actually really well in time. Let me show you the last slide of my lecture. There's another question. Can there be atom interaction in quantum walk? Well, certainly, yes. That's actually a very interesting question. Yeah, if you have quantum walks in these potentials, we have interactions, and that actually modifies quantum walks drastically. Yeah? Actually, we even have some data from a long time ago, some years ago, looking at similar things in lattices. Yeah, but that's a separate story. Okay. Let me go to the end again. I don't want to exit my. So the summary I've just told you already, yeah. And this is should acknowledge my group. Yeah, this picture is actually heavily outdated because it was taken a year before Corona, almost a year before Corona, and since then we have never come together again. Yeah, so unfortunately, yeah. So we haven't taken a group picture. Yeah, we need to do this. Hopefully in a few weeks we can do this. But let me acknowledge the people. There's Deborah Capecci and Camilo Cantillano, who are actually now the students trying to improve this system, this rubidium cesium system, yeah, that I've been talking about. And to take it to the next level. Yeah, so we've been, I have to say, the data that I showed you is a few years old, so we have been rebuilding since then. Yeah, you saw I mentioned that we have 60 laser beams entering the chamber. These 60 laser beams come from about 20 lasers, most of them diode lasers, and we decided this is too complicated. We need to simplify. So we actually bought a few commercial lasers, and we reduced the number from 20 to 12 or so. Yeah, it's not 5, it's 12 still, but it's it reduced complexity, but we are not back yet, admittedly. Yeah, so these two guys are working on it, and in fact we've just been able to get a young postdoc from India. She's not with us yet because she's in home office in India. She cannot travel. Supervising is done by Manuele Landini, the senior scientist, and I also want to acknowledge Boda Santra, who was with us until 1.5 years ago, roughly, if I remember right, and until the end of 2019, and actually worked on a different project. Yeah, so Boda worked on the single species atom experiment. We actually by now it looks like that we have also some very nice results, but the news data is not yet published. Okay, so this brings me to the end of my lecture on molecules. And again, I should do an advertisement for my friend and colleague Jun Yi, who will be talking, I believe tomorrow. Also, Martin Zwierlein, also a friend of mine, will be talking. I'm very honored to be here in this group of friends. Stefan, also a good friend of mine. Didi Leibfried was a postdoc when I was a PhD student. Christian Roos, actually, I grew up with when we were kids. So a small community, yeah. Tilman Esslinger, Immanuel Bloch. So a nice community, good friends of mine. And I really wish you a good time with all the other speakers, and you will see some fantastic results over the course of the next few days and the next 2 weeks. Yeah, I'm very confident. Okay, any questions?
Can I ask a question, Borayutto?
Yes, please go ahead.
Okay, so fantastic talk, and it's amazing to see how many lasers you have and what are the things you can do and the amount of control you have with all the lattices and all. So what is the, how is this potassium cesium going to be different from rubidium cesium? So, I mean,
yeah, good
why
question. Yeah, so actually potassium cesium was started with the goal to do the fermionic situation. Yeah, so to be directly competitive with the GILA people. Yeah. And it actually, our source is such that we have a enriched source, and we can easily, in principle at least, easily switch to potassium. But I think at the moment we're not doing this because actually the leading student is this gentleman here, is Govind Unikrishnan. You easily recognize that he's from India, and he's the most senior student right now on this project. And we decided at the moment to enter into this race of making a Bose-Einstein condensate of molecules. Yeah, so we at the moment will stick to KCS as a boson, and we have a little internal competition also, if you wish. Yeah, friendly internal competition. And I mean, rubidium cesium has the advantage that it has all components in principle working, but the electrical field control is not as good because it's still our old chamber where the electrodes are outside and not inside, and we have not rebuilt the chamber yet. That's different in KCS. KCS still needs to do some spectroscopy, and we still have to identify the excited state for our ground state transfer. But there we have a better chamber right now already with inside electrodes, and the next generation's chamber that we're working on right now. Actually, we already have a next generation chamber, but it turns out it's a glass cell with special coatings, everything, lens inside with high resolution. But it turns out we have a vacuum problem, and it's not a leak. It's an outgassing problem. That's the only reason that we can say. So we, unfortunately, we have to give up that chamber, and we will flange on a new chamber next generation where and the outgassing problem, it's a commercial cell. We don't have that under control, unfortunately. Yeah. So actually we've seen, actually Govind has seen, it's not too long ago, a few months ago, that we were able to transport ultra-cold potassium into that chamber. And when the transport worked, it turned out the lifetime in this chamber was just 2 seconds. And in the collection chamber, where we can actually also make BCs and have electrodes, we have a lifetime of 20 seconds or so. So of our cold samples. Yeah. So the lifetime gets reduced by a factor of 10, and it's evidently a vacuum problem. So we are working on this. But anyways, there is this race, I would say, yeah. Whoever's going to win it, who makes the first Bose-Einstein condensate of molecules.
So fundamentally, do you see any problem with getting a BEC of molecules? I mean, which are not, so these are composite bosons. So do you see anything different from atoms, which are sort of, we are used to
well, the
identical
fundamentally what's different is the collisions, right? And it's so it will most likely only work in 2D. Yeah, so we have to categorize the molecules. I hope you can see me in this way here, perpendicular to the plane. In fact, the nice surprise you will hear from June tomorrow. The system is also surprising. It's fermions, and that has nothing to do with being fermions or bosons, I think. Yeah, are also surprisingly stable in 3D. Yeah, so he actually they also thought it's only going to work in 2D, but they find, well, you do 2D and then you try to go to 3D, and it seems to work also. That's a surprise, yeah, because it's been discussed for 10 years now that that this might not work, yeah. Even it was discussed that even the 2D case is not going to work, yeah. So it's not. I'm not totally sure whether it's working, but I've been optimistic that we will see a Bose-Einstein condensate of molecules within the next 2 years. Of ground state molecules,
Okay.
yeah. Not we know they are weakly bound molecules, Flashback molecules, fermions, B, C, S crossover. That's all been done, yeah. But these are not molecules. Let's be honest. It's atom pairs, yeah. Extremely weakly bound atom pairs, yeah. No, I'm talking about chemically bound molecules. And yeah, within the next 2 years, I'm pretty confident that one of the groups that I've listed, or perhaps some other group that's not on my horizon, will do it, yeah. Yeah, and then we are in with dipolar superfluids that are really strongly interacting, yeah. So that will open a new door, yeah.
Yes. Okay, then thank you once again, Professor Nägerl, for this wonderful set of lectures.
Thanks a lot, yeah. Thanks a lot for having me, yeah.
Yes.